Okay, so let's start for today. Uh, take a page. So, for example, you have your data set like this. Okay. Now, for example, I do a decision tree and I say that age greater than say 35. So this is the yes branch and this is the no branch. Okay. Now, what is the average when age is less than 35? So 200 plus 250 250 only 2, right? 250, so this is the average. And when it is greater than, yes, greater than 35, then 100 400, sorry, 100 400 500 plus 60 560 plus that's it, right? 560. So 560 divided by 3, it's around, let's say, 183, right? So this is how you do a regression problem. So now if someone gives you what is the price at, let's say, age equal to 47, then you predict as 183. So your
Oh, got it.
actual value for 47 is 60. However, it's kind of an outlier, right? It's kind of an outlier. So your prediction is 183. So now since you just have one variable, that's why you're it's kind of not very accurate. So for any age, let's say if you are inputting age as 56, also the prediction will be 183 since you just have one variable. Okay.
Okay. Yeah.
So if it is the
So
actual
for n, sorry,
and this is your predicted. So here age is 40, 183. Age is 30, 125. Age is 56, 183. Age is 23, 125, 183. So now your error will be 183 minus 100 whole square plus
123.
125 minus 200 whole square plus 183 minus 400 whole square plus 125 minus 50 whole square plus 183 minus 60 whole square. This will be your total error or sum of squares. Okay. So that's how you deal with it. Clear?
Yeah, it's clear. So after this, we have got all the errors.
Yeah.
Next, what means finally we have to predict.
So we have already
So
predicted
assuming this
now
is coming, yeah,
uh,
it's coming X. Oh, okay. So you mean for age greater than 35, it will be 83,
183.
and that will be our answer.
Yeah. Since you just have one variable and then this is a very shallow tree, right? So
Okay.
yeah. So if you go on
So
building the tree, then this can be, let's say, after this you take a age greater than 40 and then do an average here. And then again it can be age greater than 50. So as you go on building the trees, I just explaining how these things can be used. I mean, this decision tree can be used for irrigation. So basically, in that group, you try to take the average of the whole thing. Okay,
yes,
is it clear or any questions you have?
yeah, no, no, it's clear.
Okay, amazing.
And I have one more question basically
Yeah, yeah,
regarding confidence versus accuracy. We have predicted based on the training set, but in test set we are getting some errors, false positive results, and other things. So confidence we calculated, and we can say, okay, this much correct we will be. Is this a correct answer for this one?
Okay, so it's a good point you have got in confidence versus accuracy. So, okay, I'll try to explain this in a different sense. So, confidence is like, let's say if you are 95 confidence percent confidence that your accuracy it's, let's say, 50%. Okay, it means your, if you even take a sample, different sample from the same population, 95% of times you will end up with an accuracy of 50%. Now what is the population? A population is like, let's say your you have 100 data points, right, of age versus price. You just have collected 100 data points, so that's a sample. Now there can be 220,000, 30,000, infinite data points that can exist, right? I mean, for example, in one country you would have checked, I can say that, let's say total world's population, there can be this relation of the price of the house, and they are buying at what age they are buying. Okay, so infinite means practically not possible to collect everyone's data, right? So you just have collected, for example, you went to 200 or 200 houses and you got 100 data points. That is a sample that you have collected, right? Now, how confident are you that this sample is the correct representation of the population? That is the confidence interval, or that is a confidence, right? So you're 95% confident that this sample that you have picked up is a representation of the population. Okay, and this accuracy that you have got 50% or 20% or 100%, this accuracy is independent of confidence, right? This accuracy doesn't have to be related with the confidence. Accuracy is an independent factor. So accuracy will tell that how accurate you are on the model. Confidence will tell that if you get a new sample from the same population, 95% times your accuracy will be 50%. 5% of the times you can't say. It can increase, it can decrease. Basically, your model that you have fitted, the y is equal to fx on a sample data, right? You fit this model on a sample data. Now, this gave you a 50% accuracy, right? Now, someone may
Yes.
challenge you that why did you take these 100 people? Why didn't you take up 100 people from India? Or why didn't you take 100 people from Afghanistan, right? So you would say that I can't go to India and Afghanistan and check what is the response. So you say that I am 95% confident that this 50% accuracy is will be true for 95% times. 5% and I can't say. And how does this come? This comes from the variance. Now let's not go into too depth of statistics, but let's, if you want to understand, if it's just a normal distribution, if you remember our class of
Yes.
the first class, this
Bell curve.
bell curve, this covers 95%. So you say that if you pick a sample from here, or if you pick a sample from here, or if you pick a sample from here, or if you pick a sample from here, all these are data points, right? So if you pick a sample from here, 95% times, based on the variance, I can see my sample will give me 50% accuracy. Okay, but if I pick up people from, let's say, India, or let's say people from underdeveloped countries, let's say whatever, let's say Afghanistan,
Go for Nepal.
Nepal or
Yeah.
Afghanistan. Okay, so that time my model may fail. I don't know. Okay, but India, maybe for example, in villages, this model will fail because I didn't consider that sample. So 95% times I am correct that 50% my model will have at least 50% accuracy. And this accuracy can be anything, 100%. It cannot be 100%, obviously. Sometimes it can be 90%, it can be 20%. It just says how confident you are in stating that accuracy. So this confidence
Okay,
interval
got
you
it.
might see a lot of times in, let's say, um, whenever you are reading medical journals, right? So medical journals, when they have a test, for example, lung cancer does smoking cause lung cancer? So every time you will find a p value there. If you ever see those journals, you will always find a p value. So they will state that p value is 0.001. So p value is this, basically this. So in case of 95%, this is this is 5%, so 0.05. P value is 0.05. So 5% times it can fail. And if a p value is less than 0.001, it means this is how much? 99.9%. So 99.9% times you can be sure that lung cancer is caused by smoking. Okay. Now, if you ever read a medical test or a medical study, you will always find this p-value quoted in any statistical test. Okay, is everyone clear?
Yeah, that's clear.
Okay, great. Okay, so now I have a quiz for you guys, a simple quiz. We'll check how good you have understood the concept. Let me open it. Very simple, small quiz. Huh? Just a second. Gmail. Oh, switch. I'll just stop the broadcasting. Okay, we can start. Okay, can you see the questions? Okay.
Yeah.
What is machine learning? First question. Ability of computer to learn from data, highly efficient search algorithms, ability of the computer to load and process data, none of the above.
A.
A. Any other answers? Let me mark you guys here. So we can talk over because I'm seeing on my iPad. You can tell the answer. So I'll mark you guys. Let me draw also. Anyways, it's not allowing me to draw here. I think. Okay, I think save a copy. Yeah. So uh, Krishna, uh, Sunil, and Sharad. So any other answers? All are saying A.
Yes.
Okay. Which of the following are necessary conditions for applying machine learning? A pattern should exist. The pattern is unknown. There should be lots of data. All of the above.
A.
D.
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 Okay, Krishna, you saying A. Sunil and Sharad D.
No,
Yeah.
D. D for dog.
Yeah, I
Yeah.
got it. Yeah,
Billy. Yeah. Okay.
Krishna is A. You want to change, Krishna?
Pattern is unknown. That is unsupervised learning, right? Yeah, I might change. Yeah, sorry.
D. Okay.
Because B was the point, right?
Okay. I'll also, I think first question is correct for everyone. Second question, I'll clear out the confusion. A pattern should exist. That is true, right?
That's
If there's it is completely random, you cannot apply machine learning. The pattern is unknown. The pattern is unknown means when we discussed that gx is a God's function, right? So we never knew that g, right? That's why we are fitting machine learning. It's not about unsupervised learning. Unsupervised learning also has a pattern.
okay.
And in supervised learning also we have a pattern, but the pattern is unknown in both cases, right? If we know the pattern, then we have the function, right? So we don't need to do anything else. So the pattern is unknown. That is one very important factor, that you don't know the pattern. That's why you're fitting the model, right? There should be lots of data, right? This is one of the necessary conditions. Anyway, which of the following is an example application of machine learning? Spam filter, voice recognition, all autonomous cars, all of the above.
All of the
So
above. D.
D.
B and C comes in deep learning, and if we are considering deep learning, then D will be the answer.
Correct. Supervised learning requires only the input features, only the outcome, both the input features and the outcome, all of the above.
Supervised
Both
learning.
input C.
Which one?
Both the input feature and outcome.
Yeah.
Correct.
Yes.
Correct. Unsupervised learning requires only the input features, only the outcome, both features and outcome, none of the above.
Only
A.
the input features.
Yeah.
A.
Excellent. Which specific category of algorithms are better suited for predicting an outcome which is a number and can take any value on the number line?
Supervised learning. Regression.
Regression C.
Regression.
Excellent. Which specific category of algorithms are better suited for predicting an outcome which is a list of values?
That is classification.
Classification.
Excellent.
D.
Which specific category of algorithms are better suited for predicting the price of a house in a subdivision?
That will be regression again.
Excellent.
C.
No. Yeah.
Okay. Any confusion?
No.
Price. Price is.
But regression is part of the supervised learning, right?
Yeah,
So
yeah.
should be A and C both, correct?
Yeah, but so supervised learning has regression and classification, right? So when I'm saying
Oh, okay.
the price, that's regression only. Okay. Which specific category of algorithm are better suited for predicting the presence of cancerous tumors after processing the patient's scan?
That will be classification.
Okay. Any other answer?
Classification.
Excellent. Which specific category of algorithms are better suited for understanding the different segments among the online shoppers of a particular e-store?
That will be clustering.
Any other answers?
Clustering.
Different segments. Yeah.
Excellent. Great going. Which specific category of algorithms are better suited for predicting the stock price of a company after 3 months?
Regression.
Again, regression.
Okay. I think these are easy. Now, what does RMS stand for?
Root mean square.
Root mean square. It will be somewhere square.
Excellent.
C.
D.
RMS is an example of
Root.
dash in linear regression.
Optimization function.
It's
Wait.
right?
Cost function.
Is
Yeah, A.
Yeah,
A cost function it should be.
yeah, correct. So, so exactly what it is, you have the cost function, and then you're trying to optimize the cost function. So you can actually tell both, right? So RMSE is you're trying to, I mean, differentiate and minimize. So optimize as in minimize here. Okay. So, but that's correct. You, if there are two things that cost function is a better one to write down. Okay. So optimize as in you are kind of minimizing the cost function. Okay. Which of the following library in Python implements the machine learning algorithms?
D scikit-learn.
Right? NumPy.
No, machine
Learning, yeah, NumPy.
scikit-learn.
Yeah, A.
NumPy.
MCAL is the data.
Scikit-learn, scikit-learn. NumPy is for basically plotting, Panda for creating metrics, scikit-learn is for machine learning algorithms.
Excellent, Sunil. Yeah. So let me write here. NumPy is data handling. Okay. So you can have your arrays or matrices. Okay. Then scikit-learn is your machine learning packages. Are, remember, every time we write import sklearn, import decision tree from scikit-learn. So scikit-learn is where all the packages of machine learning are there. Pandas is the data frame, in which we kind of store the data. Matplotlib is a visualization. Okay. What does the coefficients of a feature imply in linear regression?
A significant that feature towards the outcome.
Positivity, yeah.
Or
A.
D, A or D, let me think, significant of the feature towards the outcome. Insignificant. No, A should be the answer.
A.
Any other answers? It's actually D. So if it is very small, what is what does that mean? If your coefficient is very small,
Only confusion is with B, insignificance of that feature towards the outcome.
so that's what, right? If your out coefficient is very small, it means it is insignificant, right, towards the outcome.
Right.
Okay, then D.
And positive negative correlation, you understand, right? Positive and negative, if the coefficient is positive or negative. Okay.
Right.
Okay. Any doubts?
It's clear.
Okay. Which Python library
This
can
should be D.
Yeah, this is easy.
Matplotlib, it will be.
Load data from anyways. This is easy. Math pandas. Scikit-learn is built using. Okay, we have not seen this, so I'll mark scikit.
Yeah.
What are the key advantages of scikit-learn? Easy to learn, supports common machine learning algorithms, provides data processing capabilities, all of them.
All the above.
All of the above.
Yeah.
D.
What is this code function? A numerical representation of how good the prediction is. Another name for our root mean square error, also known as a cost function. All of the
All the above.
D.
correct.
All the above.
So I'll not agree with this. Also, another name for root mean square error, because there are many other code functions also. So, but okay, given the choice, D is a better answer. Which of the following is not a hyperparameter of a linear regression in scikit-learn? Okay, this is interesting.
Hyperparameter.
Yeah, this is interesting.
Not hyperparameter, okay? Data we have to
What is
we have to normalize.
hyperparameter?
So hyperparameter is basically the number of trees, the depth of the trees, like we discussed, the intercept. Okay,
Not
What is this copy underscore X?
Yeah.
Right.
so it
Interception.
creates different copies of features. Okay, I'll simplify the answer. Pruning. When did we do pruning? We did
We do
pruning.
in decision tree.
Yes, pruning and decision tree, right? So pruning cannot be done in linear regression. So even if you don't know the others, you can just easily answer this by saying that pruning. Oh my God, pruning was for decision trees. I cannot do pruning in linear regression, right? So if it's not a hyperparameter, so it is an easy answer to give. Okay. What is the key difference between linear regression and polynomial regression?
They are the same for me.
Higher,
Higher order of feature
B,
B.
B, sir. B.
that comes in polynomial.
What is the main advantage of linear regression?
Crazy. A B or C?
B. We don't know what he interpreted.
I think so. A should be, if given answer, A should be, but I'm not sure. D can also be.
Interpretability. Interpretability means, for example, in decision tree, if someone says, what is the partial effect of a variable, can you say that? What is the, you can say what are the important variables. Can you say what is the partial effect of a variable? You can't say, right? But
No.
in
No,
linear
because
regression,
there is only one. Yeah.
yeah, in linear regression you have the coefficients, so you can say that if I change unit of this, my output will change by this number, this unit. So that interpretability is a very big advantage of a linear regression model. Okay.
No, I didn't get. So what you're saying that there is how the interpretability means that
So
effect
for
of
example, your boss
partial
asks
effect.
me,
Hmm.
this is, let's say, price, or let's say age, and this is work x.
Mm-hmm.
So if a boss says, you have an equation to tell your boss, right? You can show an equation. Did decision tree give you any equation? No, right? It didn't tell you any equation. It is always a process, right? So
Process,
when there's
right.
a process,
Mm-hmm.
then you can't tell your boss that this is my equation. You feed in your data, and this equation will give you an output. Or you cannot say,
Mm-hmm.
like for example, 1 unit of change of x2, what will be the unit change in y, right? You can tell here, right? B1 will be the unit change, the P1 will be the change in y when I have a unit change of x2. Okay. But in decision tree, if someone
Right.
says that what is the change in work x, you have to say, okay, wait, first I have to do the prediction in both cases, and then I can tell you the outcome, right? So that's where the difference lies. Linear regression is very easy to interpret, and it has an equation form, so an equation form is always appreciated. Okay.
Okay. Okay.
When does linear regression starts failing?
C, a large number of features.
Large number of features.
Yeah.
Yeah.
What technique is used to increase the accuracy of linear regression?
RMS and switch.
Why did we go for Ridge and
Yeah.
Lasso?
RMS.
Yeah, RMS.
RMS,
RMS. Yeah.
Correct.
RMS is not a technique, right? RMS is a number. It's a score function. That's what we answered in the previous questions.
Then
P,
regularization then.
Yeah, regularization, right? That's why we went to Ridge and Lasso, because we thought that your linear regression may not do good. That's why I went to Ridge and Lasso, and that's why regularization is important to prevent overfitting. Okay.
Yeah.
Okay. Just give me a 2 minute break. I'll just join in 2 minutes. Okay, so let's start with our project today.
So before we go on to that, I think Sunil started that. I just have to clarify our understanding.
Yeah.
So for regression, we had the linear, polynomial, ridge, lasso, KNN, random forest, decision tree, and SVM. These are all the linear regression
Don't say
algorithm,
linear
right?
regression. Linear regression is a linear regression model. Regression. Okay. Let me draw this, and you can take a picture of this. Okay. So that, or I can share you the
Yeah.
image with this, so that it
Yeah,
doesn't.
if there is a cheat sheet of on this, it'll be great because
Yeah.
like
Yeah. Mhm.
Okay. I think cheat sheet you can find
Google.
in it. Okay, I think I will have an image. Not able to find it right now. So I think yeah, this one. The whole image is not there. Uh, this is one of the cheat sheets. I'll try to find out the main image. Meanwhile, do you want me to draw it, or if I send it, that will be okay?
Yeah. If you draw it, it will be, draw it. I
Okay.
think it will explain us more here. So just draw it and then. Well, we have learned so much, and a little bit confused. Like yesterday when you were asking, so probably it was more confusing.
No, no problem. Okay.
In the interviews, since you might have attended or might be knowing, so
Hmm.
what kind of questions it asks? Basically, they go through these concepts. They will give you some algorithm, and they will ask, okay, explain me about this algorithm, and tell me whether it can be used in regression versus classification, and they'll ask you to write some program. What exactly,
Okay.
or
So,
you are going to discuss later on? Then probably we can discuss later. But
okay. No,
just to
that's
think
okay.
that this is the right time we can
I
discuss
can
today.
tell you what. Just a second. I'll open my iPad. So interviews, if I may say, if you have got understood the theory of each of the models that we have done, if you have understood the theory, then you can clear any interview at this point of time. Okay, so the main ask in interviews is, what is the concept behind the theory? See, that's when Sunil was one day we had a discussion of how is theory really important, and so uh, that's why I have predominantly focused on the theory, because that's what people appreciate and that's what people will like. If you understand the theory properly, right, there is no one can challenge you. Just a second. Yeah, no one can challenge you in that, if you know the if you understand the theory well, right? See, coding is important, I would agree, but codes it are like is something like, right now anyone can write seeing the internet, right? But for example, how to tune the hyperparameters, why hyperparameter tuning is important, these are things that are, just a second, let me connect my iPad one second. Okay, so I'll draw this, and we'll have a proper understanding. So what are the algorithms that we have learned in unsupervised?
Only one algorithm, and that is k-mean.
No, clustering.
K-mean clustering.
Two, we learned two. One is the k-mean, the other one is the L something, right? I forgot the name.
This is the k-means, and then there was hierarchical.
Hierarchy.
But they're the same, right? Clustering only. These are the ways of doing a clustering, but essentially they are same. This is the process, but clustering is mainly the unsupervised part that we have learned. Now, machine learning will have regression, and then it will have classification. Now, regression, one is linear regression,
Mm-hmm.
one is polynomial
Polynomial.
regression. Linear regression improve accuracy. You go with the regularization, so ridge and lasso, but it's essentially still linear regression. Just
Oh, okay.
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 Then we learned what else. So
Here, I think KNN can be used for this.
wait. So linear regression. This is the linear part. Okay, so all these are linear. What linear means? Your When you will be fitting your line, it will be a line. It will not be a curved thing. Okay.
Time.
Now,
Correct.
when you
Correct.
start with polynomial regression, let me write it below.
Mm-hmm. Yeah, it will be an equation.
Now I start with non-linear. Okay,
Mm-hmm.
non-linear regression. So non-linear regression will have polynomial,
Okay.
k nearest neighbors, decision trees, random forest, boosting, SVM, and what else did we learn?
Neighbors,
Neighbor
neighbors should learn.
regression, I think. Yeah, I think essentially these are the things we learned in regression. Okay, so these are a part of the non-linear regression.
Okay.
Is this clear now? Do you have any questions on this?
Yeah, so I have a question that for some of them, polynomial, definitely we can draw an equation.
Yeah.
For KNN,
You cannot have
can
any
we draw? Yeah.
Does not.
So why it is called nonlinear regression?
Okay. Okay. So when you have a linear regression, you're kind of fitting a line, right?
Correct.
When
Correct.
you have a polynomial regression, then you're kind of
The fitting is for.
But since
Right.
you don't know what will be the optimum order, there can be infinite possibilities, right?
Mm-hmm. Okay.
So that's where
Mm-hmm.
your tree parts come in, or KNN comes in. So KNN, what does it do? It kinds of these are the decision boundaries. So for example, if this is a decision boundary or a curve, what does KNN do? It separates the segments. And if you remember the Voronoi diagram that we saw, I can't really draw that. I think it was something like this. So these were the splits done by k nearest neighbors. So all that who are come here are average of this. All that here are average of this, average of this, average of this, average of. So this, do you see this as a linear boundary? No, right? These have has many splits. It's
No.
kind of a curved boundary, right?
Correct.
So that's why when the boundary is curved, or we're not trying to fit a line, but doing partition, that's part of a non-linear regression. Just understand this. You're not kind of fitting a linear relationship between x and y. X and y are not directly a linear relationship. Here it's not a linear relationship. We didn't fit a single line here. We are fitting, splitting, and all. So it's a go around.
Yeah.
You don't, when you don't have these things, what you try to do, use your data and try to split it and see. That's what KNN is doing. That's what decision trees are doing. That's what the random forest is doing. So all these are part of non-linear regression.
So, but what you mean is because the boundary lines are not linear, so it falls into non-linear.
Not exactly boundary lines. Boundary lines here are linear actually, but if you could say that the whole thing. So can you just let's say this is y and this is x. Can you say y is some ax plus b? No, right? You cannot say here, because
No.
here if you here x, y is an average of all these x. Here y is an average of all these x. So I did not fit a line of sort of this, right? I did not fit a line. It's kind of a different approach that I followed. Seeing the data, I am taking an average of the more closer data points and taking an average, hoping that my that part is represented by that average. So whenever you're trying to fit a line, that's a linear regression. So Ridge and Lasso, if you remember, Ridge and Lasso had the same form of equation, right? We did not change the form. What we did is we had the score function.
Correct.
The score function had RMSE for linear regression, but then I introduced the regularization part, right? I did not change the form of the equation. Okay. So Ridge and Lasso still lie as a linear regression. Okay. But when we go into non-linear regression, so for example, polynomial, KNN, decision trees, these are all trying to fit the data and partition the data space.
Okay. So another dumb question. Here you have written all this decision tree, random forest into one line. Is there any specific reason, or just wrote it like that?
Yeah. Okay.
So these are the different algorithms, right?
Okay. SVM can be here. Decision tree, random forest, and boosting. These are all tree-based algorithms.
Oh, okay.
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 So random forest is an improvement of decision tree. Boosting is an improvement of random forest. That's what.
Oh, okay. Same category. Okay.
Yeah.
Got it.
Called tree-based algorithm.
So in case if we need to start, then we'll start with decision tree. If we are getting the good accuracy, we don't have to jump to the next one, right? Something like that.
So, okay. Now, what I would say is start with the linear regression with a ridge or a lasso. If it doesn't go well, then start with a random forest and then go with the boosting. This is for the regression part. This is mainly you should do a regularized linear regression as a first trial.
Okay.
Then you go to a random forest. Take out the important features that we saw. Again, do a random forest, and then go. I mean, after you have got the features, and then do your boosting. Normally, Boosting will give very good accuracies. Boosting is kind of an end point of machine learning. So there are hyperparameter tuning that we saw. So hyperparameter tuned boosting is very good. Sometimes, I mean, very often it beats deep learning in terms of structured data. Okay, so if you have a structured data of, let's say, 10,000 or 20,000 points, it doesn't really make sense to go for neural networks, because neural networks are good for unstructured data, but for structured data it's always better to go for boosting. So there's a algorithm called XGBoost. Read about this. Okay, if you read about this and come back to me with the doubts on this XGBoost if you don't understand. So it's a very interesting algorithm. It wins many Kaggle competitions. People use this widely. The only problem is that it is not very interpretable. That's why industries, if your boss says that no, I don't want to understand boosting, it's not very interpretable, he may constrain you to random forest. But boosting is a very good algorithm to do. And okay, I'll next class I'll teach you something called ensembling. That's not our part of the course, but I'll teach you something very interesting. Ensembling and stacking. These are two methods how you can improve even more of your accuracy. Ensembling and stacking. It's very interesting. So, next class I'll teach you. Just remind me that, since it's not in our PPT, so I can tend to forget. But remind me this. So uh, and also you can also try SVM. So XGBoost and SVM you can try. So SVM, I told you, right? If there are circular data, no algorithm can help you except SVM. So XGBoost and SVM is a good combination of algorithms. Okay, so this is where you finish regression. Now, is there any confusion?
No, I think this first will explain, because kind of a summary.
Yeah, ask any questions. You may not be. Don't think what is a dumb question or a good question. Just ask, because
Yeah.
yeah.
Okay, two questions I have basically.
Sure.
A regularized linear regression means just one line.
Yeah,
First point you have written linear regression, I understand.
Huh.
The regularized means data, if that is clustered one place, we have to regularize it.
No.
Is it, am I right? No. Or some features you have to drop.
Yeah, some features you have to drop, right? So when we said we are doing a regularization, we introduced ridge and lasso, right? So what was ridge doing? It was kind of constraining the coefficients to be very high, so that it does not overfit. Lasso, what it was doing, it was kind of dropping the
Dropping some.
Yeah, unnecessary.
Correct.
So it is trying to prevent overfitting.
Got it. And one last question.
Sure.
Hyperparameter. Just I want to understand once again.
Okay, hyperparameters are parameters which are inputted by the not inputted. There's nothing called input. Input by the user. So, for example, KNN. KNN. Do you remember 357?
Yeah.
Giving the number of
K was given by the user.
Exactly. So, did anyone tell you to give 3, or did anyone tell you to give 7? How were you deciding?
Yeah, I think so. Someone has to give.
No, so no one will give you. No, who will come and tell you that you have to use 3, 5, or 7?
Otherwise you have to try by yourself. Means random number we have to take.
No, not
right?
Random number. So what did cross validation teach you? What were you doing in cross validation?
Okay, in cross validation we were taking 4.
Sorry, Sunil, I lost you. I was not able to hear you. Come again.
Okay, in the cross validation there was a number. Based on that we were breaking the whole training part, and then training and testing, and then after that we are going one by one.
Okay, so basically cross validation, what you are trying to do is you are inputting 3, 5, 7, 9, 11, 13, and try to see the
Yes,
accuracies of each, right? And then according to the highest accuracy you are choosing knn of k of knn, right?
correct.
So hyperparameters are parameters which are not given by anyone. The user has to tweak those and use it to find the best model possible. So if you remember in
No,
boosting,
God.
we were doing number of trees, max depth, right?
Yeah,
So
now I remember everything. Yeah.
Okay. Any other
Okay.
question? I'm very happy
No,
that
not
you
now.
guys are asking questions today. So I mean, it will clear every concept that you might have missed, or I mean, there's any confusion if it is left. Okay.
So one question. This
Sure.
is little outside.
Yeah.
So this is all the models we have, or there are other models also in machine
So,
learning?
I would not say that these are the complete list of models. There are splines. Splines is a part of polynomial regression. So there can be variants of these. So for example, if would have taught you linear regression and never taught you ridge and lasso, I might have introduced the regularization concept, but I might not have taught you ridge and lasso. So I would say that models do exist like ridge and lasso, but it's the same form of linear regression. So there are variants of kind of the same. So for boosting, for example, boosting itself has three type of boosting, right? But they all come under the umbrella of boosting. Okay, so there's something called ADA boost, there's something called extreme gradient boost, then there's called light gradient boost. Okay, so there are three or four types of boosts that are available, right? But they come under the same concept of boosting. Okay,
So that what you're saying is they are all like subset of this,
exactly.
right?
Yeah, exactly.
This is the main one, and maybe they're a subset inside this one.
Correct. Okay.
Because I was looking at something and they were talking about fuzzy logic, all that kind of things. So
Okay.
that's what I was.
Fuzzy logic is something different. It doesn't come much into machine learning, right? Fuzzy logic is kind of an simulation algorithm, right? So machine learning will have these concepts. But a fuzzy logic is a concept. It's not a model actually, and it is more kind of used in simulations where the patterns are known. Here you don't have patterns, right? So that's why you're trying to find out the patterns. But when your patterns are known, I think that is used for simulation. I'm not very uh, aware of the fuzzy logic part, but it's not a model for sure.
No. But the model will be using it somewhere, right?
Yeah,
That's what I'm.
it may be using it. Okay, any more questions?
So you mentioned that we start with the regularized linear regression, that means ridge and lasso, and then after that we should go to the random forest and boosting, and then what about the KNN? Another thing, those things when we should think to apply.
Okay, a very good question, I would say. So, okay. Now, if you guys are clear on this, then I'll start on extending some of the important concepts, which I mean are important in modeling. So, something called stacking. So, for example, you have 10 features. Okay, x1, x2, x3, x4, x5, x10. Sometimes what happens is that you have done a lot boosting neural networks, everything possible you have done, but you're still getting some, let's say 75% accuracy. So what you start to do is you start to engineer new features. What does engineer new features means? Apart from the features you have, you try to build on new features. How do you build new features? One way would be take modifications. Let's say x3 and x5 you are there. Let's say can I take x3 by x5 or x3 into x5 or x3 into x5 square or x3 square into x5, right? So you can start building
Okay.
on features. So for example, last time when I last class when we were discussing about lead time and shelf life, okay, so
Mm-hmm.
if your lead time is greater than shelf life, then your expiry probability will be always equal to 1, right? That's how it
Mm-hmm.
will I mean, that's what I know from the business. So this feature engineering can be done by
Right.
business knowledge, right? So if you understand that what could be the relation between these two, so I understand if lt by shelf life, so if I take lead time divide by shelf life, and if it is I do this, and then wherever it is less than 1, let's say it's 0.9, or let's say if it is greater than 1, whenever it's a 2 or 4, then I think I will 100% it will help my model to predict the expiry, right? But many times you don't know all these things. So what you do is you generate new features. Now, how to generate new features? What if you don't know all these business knowledge, right? So what you do is you use simpler models to generate features. So, for example, you have used KNN, you use KNN on all these features that are given, and whatever the prediction of KNN is, you add that as a feature. You don't add that as an output because you know KNN output will not be very good. Okay, so you add that as a feature. So, for example, mm, let's take this example of that we have been continuing work experience, age, and what was the third thing? I always forget the third one. Anyways, price. Okay. um age, income. Yeah, income. So for example, you have data on this. You kind of have all the data, you have all the prices, this is your training set. Now what you do, you say that you have tried everything, you not getting much beyond that. So what you try to do is you build price by KNN method. We have this feature and kind of you use this set, whatever set was given, apply KNN and do a prediction on this and add this as a feature. Are you understanding? You have the data,
Okay. So
KNN you apply,
probably KNN is introduced to add new features. That's
correct, predict,
we.
and
Yeah.
then
Okay.
add the prediction. Add is not numerical add, append the prediction to the original data. So it kind of gives your model a direction that the model will know that KNN is not the best model to deal with, but KNN will give it at least some direction on the sense of what the data is telling. Okay, so this process is called stacking. Now, this stacking can be done with any model. So, for example, you can do a price by KNN, then you can also add by price by decision tree, then you can also do a price by boosting, okay, and then you apply a different model on all these things.
So it's always used in combination of one of these thing. It's not used standalone. Is that the right assumption?
Uh, that's what I have come across, right? KNN is not very useful in actual modeling, but KNN is very much used in feature generations. feature generation.
Okay. Okay. Mhm. Okay.
This process is called stacking. Okay,
Got. Got.
stacking is a fairly new concept, huh? So I think this is you might be very happy that you are almost latest. You have the latest updates, whatever is going in machine learning. Stacking is a very new concept. So people, do experiments with models. So there's something called ensembling also that I told you. Ensembling, I will not confuse you much. So it is basically what happens. You have a boosting model and you combine with an SVM. Okay, so you have multiple models and you combine the models into one. So I'll not go into depth of ensembling, but stacking. Since you asked that, stacking I introduced. Okay, so okay, now since this is clear, we left with I mean, we didn't discuss classification.
Mm-hmm.
Right? So classification. Okay, tell me which ones we did. We started with logistic. Okay, first we started with KNN.
Logistic. Yeah.
KNN can do a classification, and logistic can do a classification. And then what else? Knife based.
Decision tree.
Yeah, we'll do that. Tree based, DT, random forest, boosting. Okay, what else?
I think SVM can also do.
SVM, correct, amazing. What else? Last night we learned LDA, right? And yeah, I think so. That's it. That's what we have learned in classification.
So similar question. So if we know that this is a classification problem, then how should we start? Which model we should start with, and then how to
So
trace?
start with logistic,
Okay.
go to random forest, and then boosting. So boosting again
Okay.
will
Similar thing. Yeah.
perform the best in classification problems.
Okay. Got it. Similar. There we start with linear and then go to the random forest and boostings. And here we start with logistics and then go to the random forest and boosting.
And these can be used
And
for
then this
feature generations.
Naibase and KN, and these can be generated for the feature generation, right?
Yeah.
Okay. What about the SVM support method?
SVM also okay. So SVM, I'm saying said right. It's not a bad algorithm. It's not a weak algorithm. It's a very good algorithm, very powerful. But uh, it may help you a lot when boosting cannot help. So SVM, you have to always try. SVM always has to be tried once. Okay.
Yeah, this is really good. This is the kind of questions that we had because we have learned so many things, but where when to apply, which one to start with. Yeah.
I understand.
Okay.
No problem.
Yeah.
Okay.
Good. Thank you.
Yeah, no problem at all. Okay, one more thing I had in mind. I'm forgetting it. What I wanted to tell you. Hmm. Linked. Okay. Anyways, we can. Just, anyways, I forgot what I wanted to tell you here. Anyways, any questions? If not there, then we can start with just an overview of the project. We'll not uh, do hands-on. So next class, what you can do is do did you guys do that hands-on? What I told that try that Boston dataset with different hyperparameters of boosting.
No, I didn't.
So not in detail, but we went through few plottings and other things.
Yeah, next class do that. Okay, boosting uh, with cross validation. so that it's a hands-on for you, right? Boosting with cross validation and finding the best number of trees. Okay, do this for next class. Anyways, so any questions till now?
So regarding today, we were planning Shobhit, that we will go for a project work. So
Yeah.
what are we doing exactly in that?
So we have a sample data, and I'll show you what are the general steps that you should take and how you should proceed. So
Okay, okay, I'm waiting.
okay, so if there are no questions, then can we move on to that?
Yeah, yes, from me.
Yeah. Okay. Then I'll start from here. So this is kind of a simple problem. Let me show you the data set. Why it's not happening? Anyways, so I think what we can do is we can see it from here. So these are the different loan IDs, and then you have the gender, then you have whether they are married, then there are seeing you are seeing the number of dependents, then you are seeing the education, then you are seeing whether he or she is self-employed, then you are seeing the income of the applicant, then you are seeing the co-applicants. So there are multiple applicants you take as a I mean, if there are multiple applicants in the loan, and then the what is the loan amount term, how many months he is taking for credit history. If it is he has defaulted, then 0. If it is not defaulted, then 1. Property area, which property he belongs to, gender, married, prop area. What is this prop area? I'm not sure about it. Just a second, I'll open the data dictionary. So why it's not opening? Yeah. So this is the data that we have, and let me see. Okay, it's not there here. Anyways, so not required. So basically, you want to predict. This is the X part, where the predictors based on your ID, based on your these parameters. You are trying to predict. Let me open the Y. So whether this guy will default in the loan or not. Okay, so this is a typical data set. Okay, now I'll tell you how to approach some of the methods that we didn't discuss. The modeling part will not discuss because modeling we have already done. So you will not go into details of what model, why we applied this model, or what all models we applied. This is more of a sample, but you can, whatever models we have discussed, you can go on and check the other models also. So you basically, this is the reading of the data, and this is the reading of the Y data. Now, first part is label encoder. Now, if you remember that a gender, for example, gender is a categorical variable, right? So you have to
Yes,
first,
sorry, sorry, one question. So what is our problem statement? Whether he will be defaulter or not?
yeah.
So where is the defaulter? Means
That's what
previous defaulters I want to see.
this is your data, right? These are the previous default.
This is the data, I think, yeah.
This is the data, right?
Where it says that based on these things, this is your.
There was some defaulter.
Yeah, just a second.
Where is defaulter?
This in a different,
This what you are sharing with her. This is the training data, correct?
yeah.
Okay.
And where is a target basically in this? Okay, this is target. Okay.
Different file. That's why it was in a Y train. It is now here. Okay.
Okay, so we will get some new data, gender, married, everything, and we have to decide why.
You have to decide whether he'll default or not. Okay. So this is your training data.
Yeah. Okay.
Okay. Got it. Okay. I'll remove this
Yeah, that's
because
clear now.
otherwise it will create a mess in my code.
Okay.
So first,
So we have one more question. I think me and Sunil were discussing. So when we start with any machine learning, and if we have suppose 100 data, then the training data will take the 70-80% as the training data, and the rest 20% as the testing data, or it will be otherwise around.
okay. So see, it depends on the business. So for example, if your business is saying that just give me the model, I have a separate test data that I want to perform. Okay. So you just give your best model according to cross validation on your training data, and then ask your business to give the other set of the test data. If you don't have a test data, then do an 80-20 split.
80% training and then 20% testing. Right?
Correct. And do it selected randomly. Don't select it according to the sort.
Okay.
Okay.
Got it. Okay.
Now, first of all, is to understand the data features. Have you understood all these features? What do they mean? Except the prop area.
Yeah. Prop area, property area. I think that's also clear, right? Urban,
urban, right? So it should be fine.
Oh, okay. I think I was this one. Okay, this one is after the encoding. Okay. Yeah, then this is okay. Urban and semi-urban. Okay, this is fine. So have you understood this? Now,
and
can anyone
credit history? How come it can be 1 and 0? That means that person doesn't have the credit history. You're not measuring it. Also, you're measuring it like whether it has more than 740, whatever your
no.
What is your threshold value? Something like that, right?
First time he's taking up a loan.
Oh, okay. First time taking loan. Okay, that's fine. Yeah. Or it can be a threshold value, right? That okay. In the US, generally they have like, okay, if you are less than 640, that means they will not give you loan.
Yeah. That can also be, because I don't have the data dictionary right now. I thought that it was on that file, but it's not present. So I'll just confirm on what is.
I think it's clear. I think it's pretty straightforward. Yeah.
A quick thing. What is column I and J? Both are loan amount. What is? Can you expand J if you don't mind?
This is a loan amount of the term. This is the term, and this is
term.
okay. Fine. Now, can you tell me one thing? Do you think loan ID is important or unimportant? What do you think?
No, that's not important.
Exactly.
Yeah.
Perfect. It's a primary key of the table. So whenever you are extracting data from the database, there will be a primary key that will be associated. You guys know what is primary key?
Yes.
Right.
Yeah. So there will be a primary key associated to a what do you call a table. So a primary key will never give you any pattern because it is unique for every row and it doesn't have any pattern to itself. It's randomly generated or it may be a sequence, but it doesn't have any sense. So loan ID is not generally not important. So first step is to label encode the categorical variables. So, for example, you're married, your gender, your education, your credit history, and your property area. Um, these are all categorical variables, right? So you first of all label encoded. So your gender, you label encode; married, you label encode; property area, you label encode. Label encode as in you convert that into a numeric. Okay, so this is dependent. For example, if you can see prop area is 2 1, it was earlier urban semi-urban. So semi-urban has been marked as 1 and urban has been marked as 2. Okay, so you just kind of encode it in different numerics. Okay, now married also, you see married, it was mm,
Unmarried, married. Yeah,
yeah,
you
yeah,
just put it 0 1. Yeah, got it.
okay, because Python will not understand yes no, it has to understand numerics, but
Got it.
doesn't mean, keep that in mind, it doesn't mean that married, I mean unmarried minus married is 1. Okay, it's 1 minus 0. You
Yeah,
just have to
yeah. It's a
you just have to have a representation to feed that into the data. Okay,
yeah.
now
So, Vidip, two questions. What is level encoder? From where have you imported this one?
so label encoder is you can see this here, label encoder.
So I think it is basically you give a numeric value to a unnumeric a string variable. That's it.
Correct. So you see, it's kind of fitting, no, not fitting. Sorry, it is converting the. Well, let's say these are the your strings, and it is kind of fitting the, or sorry, transforming the string to a numerical variable.
Yeah, basically, I want to understand on which basis it will give 1, 2, 3, 4.
Randomly, whatever it sees first, it will try. I mean, it doesn't have any particular algorithm to this, so might be it's
Okay, okay,
one
that's
as
fine.
one
It's yeah, it's more like a
And it,
lookup table basically. Lookup table
yeah,
concept.
look up. Yeah,
yeah,
correct,
perfect,
correct. And it
perfect.
doesn't matter also, right?
It doesn't matter, it doesn't matter. Okay, so you have this is a very important step whenever you're dealing with categorical variables. Next is you have to plot each of the variables. So how your applicant income is distributed, co-applicant income is distributed, credit history is categorical. So credit history is, let's say you have around 410 observations in yes, and credit history around 70 or 80 odd observations and no. So this is okay. Of 1:4 distribution is not very, 25% here, then 75% is there. Not a very bad one. Sorry, 20 and 80% is there. It's not a bad distribution. Now, co-applicant income, right? These are very skewed. Okay, so you see all the applicant income is kind of more skewed towards the less than 1 lakh or somewhere around 10,000, 20,000. Similarly for the applicant income, loan amount is still kind of a little less skewed. Loan amount term is little skewed. Gender is okay. Property area is amazing. It is almost equally distributed. Married is also okay, right? But applicant income and co-applicant income, these need to be, a little bit of transformations need to be there. So I'll show you something called log transformation, or let's say what I can call Cox. So there are some transformations that are, you see, if if your if your log normal distribution is like this, after you take a box Cox transformation, then it becomes more of normal. So whenever it is skewed, it becomes normal. Okay, so uh, this is kind of important. A box Cox transformation, you can easily read it from here. So whenever you have a skewed data, you can always try to type in log transformation, in Python, and do a log transformation. Okay, so that your data is more of Gaussian, okay, and not skewed. So although I would say that it is not a necessary step for beginners, but it is a good step to follow. Okay, so it might not be.
So yeah, I'm not getting, by looking into these graphs, a lot of these graphs look similar, right? Some of them are kind of as a credit history, another thing, those are kind of two different end, zero versus one.
Because these
But
are
application
categories.
income,
These are categories.
yeah, that's fine. So I'm not worried about that. Yeah, so I'm worried about this applicant income, co-applicant income, loan amount, then a loan amount term. All of these are like that, right? Because there is a one big graph, and then all others are very small, right?
Yeah, yeah.
So what is the unique about the applicant income versus loan amount term, where you are doing this log transformation of applicant income, but not doing for this
No, no.
loan amount term?
I'm saying for everyone. I'm saying for everyone. I was just giving you an example on applicant income, but you have to do it for everyone.
Ah,
Yeah, yeah. And also, so
okay.
for example, a person with 200,000, this guy is an outlier, right? So you have to remove the outlier.
Mm-hmm.
So you have to remove the outlier because he is more than three standard deviations from your normal distribution, right? So you have to remove these outliers, but that's what I'm saying. It is not a mandate to go for modeling. You can do a modeling and then go to the required accuracy, because there are lots of algorithms which can learn to all these skewed patterns, right? If everything is normal, you will never find a data which is presented you as a normal. So for example, boosting will can take care of all these things in the modeling, right? So it's not a very important step, but it is a good practice. It's a hygienic practice to transform these data into a more suitable. So you can just read about box Cox transformation. So these are additional things that I'm telling you. Okay, so these are kind of how to improve better modeling techniques. So just read about box Cox transformation, how it does. If you guys are not clear, then we can discuss it next class. Okay, but basically I would want you to read about it. Then what we do is we kind of start with a decision tree classifier. Okay, then we what we do is import the accuracy score. So here we kind of store our model. Then we use the numerical variables, so applicant income, co-applicant income, loan amount term, credit history, and start to form a model. Okay, then you see what is the cross validation score. So cross val score, same model X train. You use the kind of what do you call the um, continuous variables, and you add credit history. Credit history is also there. So why we have not used the other variables? Any idea why?
What is the question again? Sorry.
Why I have not used married or prop area? Can you tell me in my modeling approach?
Because that is only two values, right? You have only two values.
That doesn't matter, right? Categorical variables can have only two values. Does that mean your categorical variables are useless? So why I have used is because the distribution is almost the same. So whether my property area is 0 or 1 or 2, my distribution of the data is quite similar. So I visually I can see my prop area is not very important to my model. Can you
But yeah, but your married is it's different, right? There
yeah,
is a big ratio there,
yeah,
right?
yeah. Married is important, so that I will use later. I am just giving you an example of how you can take subsets of variables and use it. But why would I neglect crop area? That's my question.
No, no. See, crop area, you're telling basically it is more or less similar, right? There is
Exactly.
what 270, 190,
So this is around
200.
140, I
Yeah,
would
but
say, 210,
yeah,
and it's almost 150. So it's almost equally distributed.
yeah, but still it makes sense, right? There might be value in it, right?
There might be
See,
value.
it's not 100% matching, right? It's not 100% equally distributed,
Correct, correct,
right?
correct. So what I'm trying to say is your visual importance, right? Visual importance will come into picture later when you will see the importance of crop area will be very less when you will see that later. Okay, so it's very important to visualize the data, and by my experience I can tell you that this distribution is very very similar. So for example, you can see visually that it is slightly different, but from my experience I can already tell you that crop area is not very useful to this model. So a difference of, let's say, 50 in a total distribution of, let's say, 500, so 10% distribution difference will not make much difference. But it doesn't have to be that you neglect that crop area initially already, right? I'm just telling you by my experience what we can see from the data. So if this is kind of similar, that means you can completely neglect that. If it is almost similar, let's say if it is 150, 150, 150 everywhere, then you can neglect that variable straight away.
So from this property area, it means we have only three areas, right?
Yeah, it's only 3 years: semi-urban, urban, and rural. I think so.
Okay,
Semi-urban.
because more or less all are same, so time being we are ignoring them.
Yeah. So see, my modeling here, my basic objective is to give you all the possible combinations that you can use, right? Because we have already seen how to take all the variables initially, when we were doing a decision tree classifier. What if you want to select specific variables and want to do a decision tree classifier? Okay, so that's what my motive is. And though these are not similar, so you will not never find a very equal distribution data, right? You'll not find 133%, 33%, 33%. Never it will happen. But if you could see that the distribution is such, then there might be a thinking possibility that, okay, if it is equally distributed, then it might be not important. Okay, so now what we do is we do a cross validation and apply that model on the specific variables and see the score. Okay, is this clear?
But I'm still not 100% satisfied with the data thing you talked about regarding that property.
Okay, okay, okay.
Which one?
Neglect that. No, neglect that. Um, don't consider that. If you are not comfortable with that, don't consider that. You just feed in all the variables initially. Okay, so
Okay.
it's that's what I'm saying. It's not a necessary step to do. But anyways, what was your question that is still you're struggling to
No,
make?
no, no, because it's not about the logic or anything, it's about the data, right?
Yeah,
Basically, what I'm saying is, say, for example, by my experience, there's a high possibility of rural having default more, right? If
correct,
the rural area was more, that means this particular data makes sense for me, right?
correct. But that's what I'm saying. It's a very early stage to just do a distribution analysis. It's not, you're not kind of neglecting this altogether. You're not saying that proper area is, it should not be taken. It's just a visualization. It's just an understanding how property area is distributed along your data. It's okay. It's not. I'm not saying you to neglect it completely. I'm
Okay,
just
got it.
trying
Got it.
to make you visualize how the distribution would look like.
Okay, got it.
Okay. Now you see that your scores. It might also happen that your uh, property area becomes very important. For example, if I take the yes no conditional distributions on this, then it will might give you a very different picture. So let's say, or take all the yes and take the distribution of property area, and take all the no and take the distribution area. In that case, in yes, I mean in defaults, you might see that rural people are more prone to I mean default. In no, it might be the urban people more prone to. So I'm not even taking the conditional distribution. What I'm trying to say is property area is kind of uniformly distributed. So there's a high chance that this is not very important in your data. There's a chance, but it might not be the case. I have not done the conditional distribution. Do you understand what I'm trying to say now? Conditional distribution.
I got it. Yeah, I got it.
Yeah. Yeah. Okay. So then we have a score. Okay. Now what I do is, sorry. Then I take uh, just a second. Yeah, I take the same model, and then what I initially what I had was, I had the decision tree classifier according to the a general accuracy metrics. Now I want the entropy. So you remember when we were discussing Gini index and entropy? So entropy is kind of similar what Gini index would describe, right? So we do the same thing, and kind of the same variables, and you fit the model, and you see that there's accuracy has improved. Can anyone say why it has happened? Why your entropy has improved? Because we just have introduced the criterion, right? We have not done anything else. Can anyone answer? Okay, so when we don't specify the criterion, then it takes into consideration the accuracy. But when we take the criterion as entropy, it kind of takes into consideration the probabilities of distribution, right? What we discussed in Gini index, how your every cut is kind of helping you to understand the distribution, and that way the sequence of the variables that are taken for the decision tree cuts changes. Are you following? Are you following this statement?
Yeah.
Uh, Sunil, Sharad, any question?
Yes.
Did you follow this
Can
statement?
you repeat it?
Yeah, yeah, okay.
No, I didn't.
Yeah. So, do you remember when we took the decision tree and we were cutting across the decision tree, and we remember we had to see the probability distributions. On the left side there was a
Mm-hmm.
probability distribution, on the right side there was a probability distribution, and then we were calculating
Right.
the Gini index, and then we were calculating whether this cut was very important or the cut was not important. Do you remember now?
Mm-hmm.
Correct or no?
Yeah. No, that's fine.
Okay, so if you remember that, so in that case what it was doing, it was deciding that the first variable will be decided when the Gini index drops to the maximum. I mean, the highest decrease in Gini index, it was deciding which variable to put at the top of the decision tree cut. Remember, age greater than
Correct.
40 was the first variable. Then we had work X. Then we had income. How did we say that age was the first variable? Why didn't income go? Because we were saying that with the cut of the age, I would see the maximum drop of Gini index.
Mhm.
Yeah,
Does
I
it?
think now it makes sense. Yeah.
Yeah.
So now basically, what you're saying is the first run it took in the order of what we gave. The second run it's taking based on the Gini index. That's what you're saying, right?
Correct. So in the first time, it didn't take in the order. It would take in a whatever the criterion is default. I think the criterion default criterion is accuracy. So it was testing the accuracy. But I did I say that a class accuracy is not a good measure in terms of classification, because we are doing a classification problem, right? Yes or no? And I said that accuracy is not a very good measure to build your decision tree in a case of classification, because there can be true positives, true negatives. Do you remember that confusion matrix that we drew?
I I vaguely remember. Sorry.
Yeah. So that's why I'm saying the theory part is very important. So when we guys go through all these things, that's where that important picture comes in. So why did criteria changing to entropy change your accuracy by almost 2%? I mean, 2 of total. So it from 0.71 to 0.73, right? So because your criterion now entropy does a better decision tree builder than what your default criterion is, which is accuracy. Okay, is this clear?
Yes.
Yeah,
No,
you can go ahead.
okay.
Yeah.
Now this is what you do for a min-max scalar. Okay, so for example, do you remember the min-max scalar? The min-max scalar was when we were dividing the number by the range, maximum minus minimum. Okay, I think we have to go back to the slides. Which week was it? I think.
Yeah, if you can basically, sorry, if you can basically have it parallelly to show us, that will basically give us an idea. Sorry, too
Yeah.
much.
Okay. No problem. But the problem is that we have to search where it was. Yeah, this one.
Hey, Subhadeep, you can, yeah, okay. Otherwise, you can let us know. That was very simple concept.
Yeah. This one is was min-max scalar. So what it was doing, it was kind of scaling the data. Remember scaling the data?
Yeah, yeah, we remember now.
Yeah. Okay. So you do a min-max scalar. How on which data you can do a min-max scalar? Continuous variable, right? You cannot do a
Uh,
min-max scaling on a categorical variable. So take all the min-max scalar on the this thing, and so if I do a credit history, if I do it min-max scalar, it will not change anything. Okay, but it will change for applicant income, co-applicant income, loan amount term. Okay, now you see how your score has changed. Are you following it?
Yeah, quick question. You were telling about the logarithmic this thing, right? Where did you use that one? So for the
Yeah.
applicant income and co-applicant income,
Yeah.
you were trying to use the logarithmic this thing, right?
Yeah.
Distribution.
So I have not used it. I was stating all the possibilities that you can do with.
Oh,
Yeah.
okay.
I have not used it here. I was just stating the possibilities that you can. So that comes into a part of more advanced modeling, right? So when you do a
Oh,
more advanced modeling, when you are trying to go by inch and inch of that accuracy, then you go and do all those things when you take a box Cox transformation or a log transformation to make your data more normal. Okay.
no, but I was under the impression because after seeing the visualization, to decide on what you have to do with the data.
Yeah.
It's not like that.
So see, if your data is like this, it does not necessarily mean that you'll always fit a bad model. There are models which can go around this. What I'm trying to give you here is a taste of how you should proceed. But since we have done a lot and you guys are understanding, that's why I gave you a flavor of what you can do also. So for example, you can take the same code and apply a box cross transformation and then do a decision tree classifier and see the difference of the results.
Okay, got it.
Okay.
Okay. No, my mistake. Okay.
Okay, now you do a k nearest neighbors, and I've fixed the nearest neighbors equal to 5. And let's see what is the score. See, it is so poor. It is 0.664. So that's why k nearest neighbor is not a very good model. Sorry, this one is like 0.65 for the n equal to 5 and 0.66 for n equal to 10. So it does not help. KNN does not help in prediction that much, and a simple decision tree helped. Was better than a k nearest neighbor. Are you guys following?
Yes.
Yes. Yeah. Go ahead.
Okay. Now see how if I change my nearest neighbors from 2 to 40, how my scores are varying. So after this point, it comes.
It's still not good. Yeah.
It becomes saturated. It doesn't change much. Okay.
It's interesting.
Okay, so now you see what I did is the first neighbors I am keeping the default, and next one what I'm doing is I'm keeping the weights as distances. Okay, now for example, when we're building a KNN, we didn't discuss this. So we were doing in a KNN model, we were taking the distances from the points, and we were kind of finding the closest neighbors and taking an average or the majority voting of those neighbors, right? Correct?
Yeah, that's correct.
Yes.
Okay. Now there is something called a weights. So you give more weightage. So for example, there are three points which are close to you, but each point will have a weightage. So the closest point will have the highest weightage, the second point will have the second highest weightage, and the third point will have the least weightage according to the distance. So here when I've input weights equal to distance, it means I'm giving more weightage to the points which are closer to me or vis-a-vis the points which are farther to me. So when I took k nearest neighbor equal to 5, and I had 5 data points, I gave equal weightage and I took the majority vote of equal. But when I have KNN equal to 5 and I took the majority vote for the according to the distance, so I take the majority vote of the, for example, if some first one has voted yes, okay, a second one has also voted yes, although the fourth, fifth had voted no, I'll still take the yes as the answer, because if there are much closer to me. Okay, so that the algorithm will itself decide on its own whether to cancel the majority voting and take into consideration these people, or I should go with the later ones also. Did you understand it?
Sure. Subhadeep, you mean to say if I'm the center and there are 3 points at distance, one means first nearest, second nearest, and third nearest.
Correct.
This time we are seeing their distance actually, how far point 1 is from me, not as like what the 3.
Correct.
Is it?
Awesome. Yes. So we are not just seeing top 5 points. We are also considering their ranking and their distance.
Actual distance, okay.
Yeah. Is it clear to everyone?
Yeah.
Yep.
So this will make much more sense when you are doing a regression. So when you are doing a regression and you take an average, if you keep your weights as distance, then you do a weighted average. Okay, so you give more weightage to the value
which is closer to you than to the value which is farther from you. Does this make sense now?
Yeah. So one question. So if I have,
Yeah.
so it might be possible after giving this weightage,
Yeah.
my score can go down. That can be case.
That can go.
So,
Yeah.
but that can timing we can assume.
Yeah. Yeah.
So in this case, if it is going down, which one will be better for us? How can we say? Earlier we have seen 0.73, and here it comes around 65 or 70. But now weightage, that is a very good thing we have included.
See,
So although our
slowly,
score is going down,
if your
yeah,
nearest
it
neighbor
can
is
stop.
39, it will slowly converge, because if you have 40 data points, then your closer data points will always give more weightage, and slowly it will converge to what you are initially using, right? But if you see
Yes.
the initial ones, you see there's a huge difference. One is 0.63, one is 0.64, then one is 0.68, the other is 0.64 again. Sometimes it is higher also, like this one, 0.59, this is 0.54. So when you have four nearest neighbors and you take the weightage, then it is higher than what if you don't take the weightage. So you have to see your algorithm's performance. You cannot judge it directly from
Okay.
yeah.
The other question I have, the distance you're telling is the nearest, you're giving more weightage to the nearest point, right?
Yeah, yeah.
So suppose if I want to do the other way around, if I want to give weightage to the farthest point.
No, you cannot do that, because it doesn't make sense. Your nearest neighbors means that you want to give weightage to the nearest
Nearest only.
points. That's you're taking top 3 points nearest to you.
Oh, okay.
Okay.
So there's no use case of telling, okay, the farthest point I'll give
No,
more weightage or something.
no. You can go in the package backend and change your weighting function, but that is not a use case normally. That no one does that.
Okay.
Okay.
Ashwini, one question here. So assuming I have solved this one, but my manager asked the term, how long it's the long term is. That is very important on the top priority for us.
No, I didn't understand. If your
So
manager asks what?
okay, okay. So time being, we have application income, co-applicant, loan term, loan amount. All these are of equal weightage for us.
Okay.
Means every from our side priority is one for every. As for example, do you remember that decision tree? Temperature, then
No,
humidity,
Sunil,
then
you
something else.
got this
Temperature
wrong.
can be the first criteria for me. Yeah.
Wait. You're talking about the weightage distance in k-nearest neighbors. You're saying that?
Basically in decision tree, the priority can be changed for you, and another thing can be first priority for me.
Okay.
As like humidity can be the first priority, but for you temperature can be the first priority.
So that's why random forest comes into picture, no? That's why it takes into consideration
Okay.
all the priorities, all the variables, and its top priorities.
Okay.
No, I didn't get your question. So you're saying that
My question is here basically applicant income, co-applicant income, loan amount, loan term. These are all equal weightage we have given,
correct.
and we have asked random forest to decide yourself.
Yeah.
What you do. So my question is here, assuming loan term, which varies up to 240, but 200, if this is good for me, if that is the case or not, I want to understand.
So
I want to
you cannot
give extra weightage. Yeah.
No, you cannot do. I mean, try to. This is manipulating your data, right? If your data does not say.
Yeah, I'm manipulating.
Yeah, if your data does not say that this is of more higher priority, then you should not forcefully tell it to this to be for your first priority, right? That is not a good practice to do. Let your data tell, no?
Okay, I got my answer. It is in in that case, basically first I have to manipulate my data, then I have to feed the model.
Yeah,
If that
exactly.
is the case,
Yeah.
I got it.
Okay. The third case is you change the algorithm. So there's something called a brute force algorithm. Don't go by that. Mhm. It will is not very much important. Now let's see logistic regression. How logistic regression improves your accuracy. You see how it
Oh
has.
my god, 80%.
Hmm.
Okay.
Okay. Now I change the solver. So logistic regression has different types of solvers. We come to that. I'll show you the hyperparameter. What it so it didn't change much. It's almost the same. It was 0.806 and it was 0.08. So what we have changed is a solver. I'll just tell you what a solver is. Okay. Now let's see after scaling how it improves. Okay. So after scaling, you see it doesn't change that much. Can you say why KNN changed with the scaling, but logistic regression did not change with the scaling? Okay, was it logistic regression? Which one did change after scaling? Yeah, decision tree. Yeah, decision tree changed after scaling, but logistic regression didn't change much after scaling. Why? Any answer?
Can you give me the definition of the scaling? You today morning only you told just to.
So the min max scalar we have, this is scaling only.
Oh, the min max scaling. Okay, okay.
We here we have done just a second. Yeah, here also we have used the function scale. I think scale also does a min max scale. Let's just see. Let's see. I know scale. I think does a normal scaling. Wait, just let's see scale in Python. Yeah, I got it. So I'll just think of this as a min max scalar for right now, and just tell me how do you think this min max scalar would help in decision tree and did not help in logistic regression.
The decision tree is the nearest point. Basically, you're basically finding the min and max within the cluster, right? But logistic, there's no kind of a cluster, right?
No,
Is
decision
that
tree min max of the cluster. I didn't get what you were saying. Decision tree is
so?
the algorithm which does a division on different parameters and
Yeah.
fits. Okay, I'll tell the answer. So when decision tree is kind of doing the classification or doing the cutting across the different variables, if the variables are not scaled, the variable which is high in magnitude will always be above than the variable which is low in magnitude, because the variance in that will be much higher compared to the variance in the variables which are lower in magnitude. So, for example, if something is in centimeters and something is in kilometers, the kilometers will always be on a higher spot in decision tree because there's a lot of variation in kilometers. But centimeters will be here and there, right? So, if you remember your standard deviation, your standard deviation changes. Remember from our first class, if you multiply all the way number by 2, how your standard deviation changes?
Yeah, this there's a change in the standard deviation, right?
Correct. So when you're having a higher scale of higher scale of variables, the variables which have higher magnitude will always be at the top. So decision tree gets confused since it says things, since it's a higher in magnitude, it is more important, but that may not necessarily be the condition, right? The real condition could be reversed. So that's why decision tree, we need to scale the variables when we are using a decision tree. But logistic regression doesn't have to be, right? The logistic regression can adjust the coefficient beta with respect to x. So if your x is 100 times higher, then your beta will be 100 times lower, right? It will adjust the coefficient according to the x. Are you getting my point?
Okay, got it, got it. So, but the one thing you told in the previous classes was the measure, right? The unit of measure should be the same, right? Should convert it into the same measure.
Yeah, that's an ideal practice you should follow.
Right. In that case, if the unit of measure is the same in
No.
this case,
I'm sorry, it's not unit of measure. It's, you should have all unitless. So when you're doing a scaling, everything is
yeah,
unitless. It's not unit of measure. So if it is in kilometers and centimeters, you don't need to convert the centimeters to kilometer. You make everything unitless. And how you can make that unitless is, you can do a min-max scaling or you can do a scale. Now scale is very easy. Instead of min-max scaling where you're doing an x minus min upon max minus min, you just do a x minus mu divided by the standard deviation. That is called scaling. Okay. Sharad, is this okay? I'm not hearing you much.
No, it's sorry.
No, it's okay. Yeah.
Perfect. Please let me know if it is, if there's any even speck of doubt. Just let me know, so that, because see, now you might have realized how your theory is related to all the modeling, right? So your theory comes first. Everything comes later. Your theory comes first. So everything that we are doing is related to what we learned in our first class even. That's why I would understand if you would have forgotten in the previous classes. So that's why it's very important to revise right now.
So I have a question. So in the morning you mentioned that first we need to start any model with this is a classification problem, right?
Yeah.
So logistic regression, then move to the decision tree and other thing. But you started other way around. You started decision tree and now going to the logistic regression.
Yeah. So see, that's what I know. This is someone else has given some of part of his code. I have appended. So it's not the sequence that you should follow. What I told is, you can do a logistic regression and then go for a decision tree. If you do a decision tree and go for a logistic regression, it will not make your model different. This is the sequence you should follow. Right now, I have just kept differently in a different, because these are different fragments that we have concatenated. So don't understand the sequence of modeling. Whatever I've written in that iPad, always follow that. This is for a more of an illustrative purpose. And anyways, you have to see decision tree and logistic regression and random forest and take the best of it, right? So anyways, you have to do all of it. Okay. So
Okay.
if you,
Yeah, but if you get so kind of accuracy, what we are looking for is in the 90% range, right? So as soon as we started getting that, we'll say, okay, this is the best model, something like that, and then we'll drop the ball.
it might not be key 90% is a benchmark.
So right,
It might be that even so, whatever
70% or whatever.
what I'm telling you, that your transformations are required. So if you do a transformation, your accuracy might improve. A problem which has 65 accuracy in a linear regression. Do you remember the Boston data set? It was 50% in linear regression. Lasso, it was around 48 or 50. Boosting, it went up to 88%, and we did not do any data cleansing, right? So it's not, there's no particular benchmark that a model you can, I mean, there are small things that you need to change to improve your model. But if you want to understand the best model, boosting has the highest probability to give you the best model. So always end your model with boosting. Okay.
Okay.
So we have
So
understood.
if you're claiming boosting will give the best model, then why don't we directly go to boosting?
Okay. So what I what
I,
I what I told you is you never know the God's function. If your God's function is linear, then your boosting will not give your best accuracy. Your linear regression is will give you best accuracy. Yeah. So you remember first class I said something called Occam's razor. Occam's razor is a statistical, theory or a concept. Every modeler should start with a simple model and then go on to. So, for example, your boosting, let's say if your God's function is linear and you do a boosting, you might end up in a very good training accuracy. Very good training accuracy. Even your cross validation accuracy may be very good. But if another data point comes up and you try to do a linear regression, or sorry, a boosting, you'll go very way off than what it was a linear regression. For example, let me give you an example. I'm doing a forecasting project for my company, right? So normally, let's say a product historical sales, it is very kind of a sinusoidal graph. Okay, up down, up down, up down, up down, spikes. Okay, not very smooth spikes. Now if I do a boosting on it, it'll try to fit everything, the up ones, down ones, up ones, down ones. So my training will be very smooth. My training will be almost accuracy almost, let's say, 90%. But the reality is those are noises. Okay, so those are noises because someone is doing a promotion, someone is doing pushing the sales. What my actual forecast should be, it should be kind of an average line that cuts across. So when I forecast that an average line, my error, my accuracy comes up to 70% in the future. If I do the XGBoost and try to forecast, my accuracy drops to 30%. Realize? But my training accuracy, even my cross validation accuracy was very good. So it's always better to, you know, start with the see, if your cross validation is accuracy is good in boosting and it's worse in linear regression, then you actually can't do anything and go but go by the boosting. But you should always have all the models ready and you should always proceed in that sense. Don't ever think that I've learned neural networks, so always every problem has to be solved by neural networks. Never is the case. Networks will never work if it is your data is very small and structured. If it is structured well, then neural networks will never work better than boosting. So every model is important. That's why till now, any course you enter in data science, they'll always start with linear regression. Any course, be it your Coursera, you start with the data camp, you start with anything, it will always start with linear regression and then go on to boosting. That's how everything proceeds. Okay, so I think this is also okay. Instead of a scaling x minus mu by sigma, I did a min max scalar and check. So it's you see it's almost the same, and it doesn't. So logistic regression is not helping. I mean, the scaling part is not helping much in the logistic regression. Okay,
yeah,
so
one quick question. So here in the code, right, you're written log dot logistic regression solver Newton. See what that means.
yeah, Newton CG. I'll tell you what that solver means. I'll get back to you. I'll show you rather on. So um, yeah, so basically I've told you how to do the logistic regression, how to do a decision tree. Now your homework for next week, and I would check, I would want you to fit a gradient boost on these features. Okay, whatever I've used, I'll send over the code, and I would want you to fit a gradient boost on these features and let me know how it comes, because I would not want to do every model for you. Then, so now see, you were asking me something like, so here, Krishna. Now you see when I add the prop area here, can you see here?
Yeah.
So without the prop area, my accuracy was 0.808. With the prop area, my accuracy is 0.806.
it has kind of decreased. Yeah. So that's what I'm saying. It's not mandatory that this distribution is kind of doesn't give you the right picture. I mean, sorry, gives you the right picture, but it gives you a fair bit of idea. And if you do a conditional distribution, then it will always give you the best idea. So if you do a conditional distribution, let's say on yes, you see the prop area distribution, and in no, you see the prop area distribution, and then compare, then it will make sense. So what essentially your answer would be, in rural area, right? In rural area, people are buying, or let's say taking loan very small amounts. In urban area, people might take loans in big amounts but not fail. But in rural area, you might have a tendency that you might have see that in rural area people are more prone to fail, but they are also taking less loan amounts, and that's why the company is also strict in their documentation, and that's why the default is very low. So when you know that this kid is weak, or when you, for example, you're a professor and you know that this kid is weak, you're going to pay extra attention to that kid so that to ensure that he doesn't fail. If you see the history of failures, spoiled brats will be more prone to failure than poor children. Poor children are more serious. They know that they have lots of thing to lose if they may not pay the loan. That's why they will pay, and that's why the rules are more stringent for them. That if he comes from rural area, then your his documentation should be very strong. His credit limit should be smaller than people who has. So if you compare farmer loans and Vijay Mallya, so Vijay Mallya has committed a huge this thing default compared to what farmers do, right? So it's kind of the data what it should tell you. It's not what your hunch. That's why we are learning machine learning, right? If everything your hunch can tell you or your experience can tell you, then you don't need machine learning. You can always tell that. But it is very important to understand how machine learning will help to improve your this thing. Does that satisfy you with the question? I'm absolutely with you
Yeah.
that it may not be the case every time, right? It's just not. Yeah, you cannot say that distribution will, you know. You see, if you add married also, then your accuracy doesn't change much. It's almost like the same.
My only concern is sometime in the business we know, okay, this particular future or the parameter has a is really important in the decision making, right?
Yeah.
So, and the machine learning tells that, okay, that is not the case. That's where the conflict comes in,
Yeah.
right?
So I have answer for that. So when I see the data, for example, let's see the data once. Okay. So for example, if you take the rural area per people, and let's say um, just a second. Let's say you have another column, strictness of documentation. Okay, you have not gathered the data, but you have something called strictness of documentation, and on the scale of 10 you would see that for rural areas the strictness of documentation is 10. Okay, so that way you will understand that when people are coming from rural area, the bank is kind of churning out a documentation which is much more strict than the people of urban. That's where your business insight comes in. It's a combination of these two features that results in your default, not just the sole features of property area, right? That's why your data collection becomes very important. There's some confounding. You remember that example when I gave you, shark attacks are dependent on ice cream sales. It's kind of the same example. You're saying that the rural area is more prone to default, but there's a confounding strictness of documentation for which your data is you have not collected, right? And
the combination of these two things are actually leading to, the default prediction. But again, I'm not saying that adding that will not be of value. You have to check every time. You have to add all the variables. It is always good to go in, uh, select all and then cut out from the rest, than to start with the subset. I would, if you would ask me personally, if I would start this data on my own, I would always take all the variables together and then do a feature selection and then go on to a difference. It might also come that addition of this may be important, but I have not seen that. So that's why it is always better to start with all the features and not a subset. Okay.
Yeah, that makes sense.
Yeah. Okay. Any questions?
So what is your homework you asked gradient descent to use? What was the exact question which we have taken as homework?
Oh, homework. Homework will be apply the gradient boost model on this data. I mean this data, whatever we are seeing. I'll send you the data. I'll send you the
Okay.
code. You just have to apply gradient boost. And Krishna, one more thing. So I knew this feature was not adding value. That's why I could back interpret this. Okay.
Oh, okay. Okay.
Okay. So as a starter, you may not be able to tell this directly because you never knew this accuracy, right? So don't get me wrong there, that I always say that this distribution should be neglected. Always start with that, and it's always better to see the conditional distribution. It might be that the conditional distribution is different. Okay, but since I knew this accuracy, I could interpret this in a better way.
So, so in the case of conditional distribution, if you want, we have to basically break down the data, then do the process, or is
No,
there
no,
a way in Python to
you can
basically
you,
break
you
it down?
can do it directly. You can do it directly.
In Python itself?
Yeah, yeah, yeah.
Okay.
Okay, and that will make much more sense than what it does here. Okay, so it might be the case that you are correct. Okay, so the conditional distribution will make much more sense than what it does on an overall. Yeah. Okay, so any questions, most, or otherwise we'll close today. 5 minutes discussion.
Not related. Sorry. Okay. Not related to this project, but in clustering related.
Clustering.
So suppose, clustering related project we have got, assuming in that case we learned k-mean basically, where all things are depending on the distance basically.
Yeah.
We selected some point and we got the distance, then took the average and repeated that.
Yeah.
So assuming we have got text documents.
Text documents, okay.
Text documents. One can be related with your science, one can be related with your history, geography, and other things. So in that case, first, as I think, so we need to model in such a way that we can get the distance. Am I right?
Yeah. So next class,
how will we proceed in that case?
We will have a detailed discussion on natural language processing, and I will once we do this question will be answered. So we are going to do the same thing that you told, how to classify documentation, text documentation, and understand how words can be translated to numbers. It's a process called word embedding, where you translate the words. It's not that A is 1 and Z is 26. It's not that. It's more of scientific. It's kind of creating vectors from words out of the documents, and we'll understand how we can do that and convert the words into numbers. And NLP is very interesting. My research is in NLP, so I can provide you a lot of details about NLP. I can also tell you how to combine deep learning and NLP. So my research is in natural language processing. So how we can combine deep learning and NLP. So
if you guys are interested in that, we will launch a course that combines deep learning and NLP into a 6 week course. I have to discuss with Ashok. I mean, when we can start that, but that is very interesting, and you might be very surprised in how natural language processing can, you know, give you amazing insights which numbers can't tell. So all the Amazon recommendations, Amazon reviews, Amazon is or Walmart. No, sorry, Amazon. Amazon has a website. I mean, Amazon's website. Netflix is dependent on text processing. Amazon reviews and recommendations are used for its collaborative filtering. A lot of applications are there for natural language processing and deep learning.
The natural language also uses takes the visual image processing also is a natural this thing,
No,
or
no.
that's
Image processing is different. Image processing is different. Text processing is different. Voice to text is different, and deep learning is different. So deep learning is kind of a machine learning on all these things: videos, uh, text, your image. So deep learning has improved the accuracies of these type of problems to I mean, to multifolds, and that's why all the Siri or the Google Assistant and whatever Windows, what does Windows call it? I think I have this. What is called?
Uh,
Cortana.
could you repeat this? Could you repeat this statement once again? Means natural language processing versus deep learning processing, NLP versus
Deep learning
deep learning.
is okay. How can I say? Deep learning is a method. Okay, it's not a processing, it's a method. NLP is how to change the numbers in sorry how to change text into numbers, and deep learning will apply the methods, machine learning methods, on those numbers, kind of, if you could say that.
Okay. It means if someone is saying that I know deep learning, it means he will be knowing first NLP,
No, no,
then he will be knowing the
not necessarily. The
processing.
deep learning can also be applied on image processing. Deep learning can also be applied on Boston dataset. Deep learning can also be applied on videos. So deep learning is a method. NLP is just a way of converting text to numbers or understanding text.
Okay. So I mean to say, in market it's very hype for deep learning, but it's not heard about this one NLP thing. What does this mean? NLP is not so much widely required.
No, NLP is more research. Right now, NLP is more in a research phase. People are trying better methods to, you know, uh, uh, better algorithms of NLP. But no one has said that NLP is, not used so much in the market. It depends on my friend who was in Walmart as a statistical analyst. His whole day he's doing natural language processing. Walmart's it's a multi-million dollar project on NLP. So no one says NLP is not there in the market. It's up to what your business requires, right?
Yes, and that thing we don't know.
Sorry.
So we are exploring. Okay. I need to say, as for example, to understand deep learning, machine learning basics, at least that is required.
Of course, of course.
In such a way,
No guy
if,
can tell that I don't know linear regression. I mean, he will not never ever be able to understand deep learning without machine learning.
exactly. So in such a way, is knowing NLP is required for deep learning or not?
No, not required.
Okay. So, okay, so other than that, related to this project, I have one question.
Yeah.
Just you visualize all these things over this bar chart.
Correct.
So, what about distribution? Do we need to draw a line and show the distributions, or only this type of diagram that will be enough in real projects?
No, see,
We are not on
visualization
chart or
is
anything.
dependent on your taste, whatever you want. Python is not a tool for visualization, first of all. Python is not something which you want to create dashboards or you want to show. It can create histograms, it can create pie chart, it can create, bar chart. It can do some very basic Excel stuff, but it's not for visualization, creating beautiful slides or something. It's more of the
for the modeler to understand the data or to understand the distribution. It's not for you to present your manager. Okay, if you would want
Okay.
to present something big or create dashboards, so Python has to be connected to Tableau. Tableau is a visualization software. So Python is not meant for visualization. It's more of data analysis or data modeling. Okay, so it's not there to create beautiful graphs, but it will serve your
Okay.
purpose. It can, with matplotlib, or then there's one more. I'm forgetting the package name. Just a second. One package P. Just a second. Okay, I'll come back with the name. I don't have that name. What was it called? So this is the type of visualizations you can do: a violin plot, a box plot, a bar chart, a line chart, a stack column, scatter plot, bubble plot, pie chart, and then a heat map.
Over here again.
Yeah. So these are the basic, but they don't look so good, right? Not very attractive, but it helps you to understand the how the data is. But there's one. I'm forgetting the name. Bro. Uh, anyways, yeah, bouquet is the document package that creates little, yeah, interactive data visualization using bouquet. See, this will, you can go through this. It creates good graphs. Just a sec. So this is even interactive, I guess.
So, so my question is, so we basically figure out which model to use, all that, right? So
Yeah,
once that is figured, how is it being used with the application?
application as an end-to-end application.
Yeah. So let us say in this case, right, in our example, we have this low default, all that, right? So
Correct.
this is a sample set. We take it, we figure out, okay, this model is the best. Then we tell, okay, we test it with the test data. Everything looks good. So we have this package now, right?
Yeah.
So how is this going to be integrated with the business now?
Okay, so now you have this. If you don't want to give the user, you don't have any user interface, you can have this as a backend model. Okay, so now, for example, you have trained your model now. So, for example, my friends in Mastercard, they were using such kind of a model. No, not in Mastercard. In other, Yes Bank. Yeah, in Yes Bank. Yes Bank is an Indian bank. I don't know if you do have it in US. So Yes Bank. So they had this model. So now, if any person, it was not just these features. There were many other features also. It's not just restricted, not just with these features. So now, let's say a new user comes, you fill in this feature, then it will the user will sorry the model will tell you whether this person is likely to default, yes or no. If the model says if it is he is likely to default, then you either you don't give him the loan at all, or you charge him higher interest rates. Okay, so that's how your business will use it. Or if you say that he is too likely to default, then you never give him the more. So it will save you the, I mean, if someone defaults, right, there's a huge loss to the bank, right? So either you take more, what you call the security, and I forget the term which is used in this thing, kind of a more, uh, anyway. So you ask that person to
It also comes.
keep more.
It also comes as like a risk analysis type of thing, basically.
No, this is
So
this.
generally, PayPal or this type of companies they are using. They have a different module, basically, which exposes their CPI. where you have to give all this type of data. Based on that, you can query your next questions.
Yeah, no.
Am I right?
What he's saying is, now do you have this model? How will the business use it? So the business will use it. For example, I come to you. For example, you run a bank. I come to you. I fill in all these things, and you see, your model is telling me that I am a person who is more prone to default in the loan. Okay, so you have two, three options. You can increase my interest rates. Other than that, you can ask me to keep a more higher value. So for example, I have kept my house as a security to you, or let's say I keep my car as a security for you. You may ask me to keep my house because you say that your car is not equivalent to the value that you are asking for the loan. I want more leverage, so you ask me to keep my house as a leverage. So these things will help you. So for example, imagine if if your state bank or your state bank would have been able to predict that Vijay Mallya is going to default in, let's say, 2 3 years, then I think State Bank will be in a different position right now. It has lost 9,000 crores. It's a big thing, but these are more dynamic problems. So Vijay Mallya, that time he was good. Right now he has lost all his companies and all. So more and more complex models also involve the dimension of time, right? So how your time, with
Yeah,
the time, the user is kind of behaving.
yeah,
But
that is what you're saying is once the model tells the business, okay, this particular person is going to default, you're taking a business decision, right?
yeah,
That's fine. But your model itself is to say 90% accurate, right?
yeah, yeah,
There's no model with 100% accuracy, right?
correct.
So you're telling 90% accurate. There's this 10% which might be a good business which we are going to lose, or a bad business which we are going to keep.
Correct, correct. So see that thing, that kind of uh, I mean, that kind of contingencies will be there. At least you have reached 90%. Earlier you never know. Earlier you were giving blindly, right? You were not even doing anything. Right now you have at least 90% sure that who, and then that's why your confidence comes into picture, right? So if you're 90% sure that 95% times you will be 90% accurate, then it's good. You can at least take a chance on 10%, right? But otherwise, and of course, your model will tell you if it is, let's say, 100% sure that this person is going to default. It's likely that it is not that it is likely that he is correct. But if your model, let's say, it's 60% sure that this person is going to default, then you have some doubt. He can be here or there. Then you have that element of doubt. But if your model is telling that he's going to default 100%, then there are chances that your model is not wrong that much. In certain
No,
cases,
no, but see that we are not doing in this case, right? This is yes or no, right? Kind of
no,
answer.
no. Logistic regression will give you probabilities, right? It will just not give you yes.
Oh, okay.
It will always give you, every classification problem will give you probabilities. That's why what we
Oh,
discussed, right? Every
oh,
yes or no is dependent on the threshold. So your default threshold is zero point 0.5. Everything above zero point 0.5 is yes. Everything below zero point 0.5 is less. But it can be your business decision. If you are a risk taker, then let's keep it at zero point 0.2. If you are a more risk averse, then you keep it at zero point 0.8, right? So accordingly, you can adjust your threshold.
so, and the other question is, how do you use this in a data warehousing kind of environment? Like you were talking about tableaus, right?
Yeah.
So when you integrate it, see, there's two options, right? One, I get like a transactional data which I feed to this particular package, and it's going to give me an answer yes or no, or a percentage
Yeah.
of default, right?
Mhm.
The other thing is, how do I integrate this to a data warehousing kind of solution where I can make decision from there?
Okay, so Python can has this amazing capacity to be connected to uh, backend. It can, for example, I have connected in my what do you call, office. My data warehouse is in SAP HANA. Okay, so my Python is connected to SAP HANA. I get the transactional data flowing from there. I give my predictions, and then I visualize it in Tableau. So I have an end-to-end picture to it.
So can I basically tell, okay, this is my predicted data,
Yeah.
right, as a column, and this is my actual data, and what is the difference? Is that how you predict, or?
No, so it depends on for business to business. So, for example, what I try to show is what I try to visualize is how will my expiry of slop be affected with time. So, with time, how will be my probability of expiry change from, let's say, 1 month to 2 months to 3 months. That's what I show. You could be
Oh,
using
okay.
using in a different sense. For example, in banks, you could be seeing, for example, these things you could show that these are the important variables. If you can change, for example, your loan amount, if you drop it to like what I discussed with Sunil last time, that if you change loan amount by X percentage, can that percent come back to the not default category and you can just disburse that amount. So, for example, if
Uh,
someone is
uh,
asking for 200,000 and you say that this person is going to default by 0.7 probability, and then you say, okay, what does my model tell when he asks for $50,000? Then your model says, okay, he might default just by just 0.2. Then you are ready to disburse 20,000 or $50,000. Okay. Okay, then
yeah.
let's close
Yeah,
for today.
so this last one question.
Yeah,
That's all.
yeah.
So in this, it came around 90%, or sorry, 80% accuracy. So how much confidence can we tell you here?
So we have to see that confidence function. We have to see how much confidence it is. But normally, all algorithms operate on a 95% confidence interval. But we have to see
Oh, okay.
according to that what is the default status. Okay.
Definitely, yeah, that's great. Partially means we were looking for this thing end to end where we can understand everything.
Sure. No problem at all.
So thanks a lot.
Yeah. Sure. Thank you so
Really
much.
appreciate it.
So next week, I'll talk to Ashok.
No, what about next week? You are going to inform us by Friday.
I
So,
think I'll put up a discussion on the WhatsApp only. You guys can tell that
okay.
if you want both the classes next to next week, so that we can close with NLP and deep learning on those classes. Okay.
Yeah, sure. That's great.
Okay. Great to have you guys. Okay. It was a wonderful session. We just have 2 classes left, and if you guys would love to join our NLP and deep learning, also we can ask Ashok. So NLP and deep learning is very interesting. It is going to be tough. Let me tell you that it is going to be a little tough, much tougher than what we have done. But since now our basics are clear, you guys can carry forward with NLP and deep learning also. Okay.
So why are you including NLP and deep learning all together? Why not deep learning course only? Because those are not means someone can go for only deep
No,
learning.
no, no. I will. We'll have do different courses only. NLP and deep learning. I'm just saying.
Oh, okay.
The next 2 classes
Oh,
will introduce you to NLP and deep learning, and then it's up to your choice if you want to pursue any of them in the next course altogether. But deep learning is very uh, interesting also. So it's very good to understand that. Okay.
okay, that's great. Yeah, good night.
Okay. Good night. Enjoy. Bye.